3.6, number 17, is giving us a function here, an oddly named function of r of y, and they're asking us to come up with the derivative of this. As I'm looking at this, my first inclination, my guess is it would be yours too, is that since r of y is written as the quotient of two different expressions that both contain the variable y, we probably are going to want to use the quotient rule on this. And I think that's how I'm going to do it, but it did occur to me this problem could definitely be rewritten a different way that might make the derivative easier to come up with. But, as we do in math here, guys, if we've got two different correct ways of doing it, we should get the same answer at the end, and I guess we'll find out. But let's do it the straightforward way first. R prime of y is going to equal, and here we go, the derivative of a quotient is another quotient. We start with the denominator, which is the sine of y, and we multiply that by the derivative of the numerator. So the derivative of 3 cosine of y minus 4, well, derivative of 3 cosine of y, we're going to start with the 3 again, and then the derivative of cosine of an angle is negative sine of the same angle. So I put the negative out in front of the 3, and I want to put parentheses here, guys. Otherwise, it would be really easy to forget what I'm doing, and on the next line, think that that was a subtraction expression. Okay, and I'm sorry, and the derivative of that minus 4 right there is just 0, so I can ignore that. So this, so far, is bottom times derivative of the top, minus the numerator, which is still 3 cosine of y minus 4, times the derivative of the denominator. Derivative of sine of an angle is cosine of the same angle. All over the denominator squared, so that would be sine of y quantity squared, which we kind of prefer to write this way, sine squared of y. So what does that do for us here, everybody? In that numerator, it's ugly here, but that first term is really just a monomial times another monomial. So that is going to be a minus 3, and then sine of y times sine of y is sine squared of y. Now, at the end here, I think we're going to go ahead and distribute that negative cosine of y into that binomial to get a minus 3 cosine squared of y, and then that'll be a plus 4 cosine of y at the end of that, all over again, sine squared of y. Now at this point, everybody, the calculus is done. Actually, in the previous step, the calculus was done. It's just a question of simplifying the expression right here in a way that would be meaningful. I want to make sure everybody understands that you cannot do this. I've seen a lot of calculus students cancel out that sine squared of y and that sine squared of y. The reason you cannot do that, everybody, is because sine squared of y is not a factor of the entire numerator. Now, if you were able to factor this thing and get it sine squared of y times a big thing all over sine squared of y, then yes. Because in this case, sine squared of y is a factor being multiplied by the rest of your numerator, but you can't do that right here because it's being added or subtracted with everything else that we have right there. So I just wanted to say a quick note about why you can't do that. Now, the thing that I noticed that was kind of interesting about this numerator, I'm not sure this is going to lead us very far, but in that numerator, I'm going to factor out a negative 3 just from the first two terms. And that's going to leave us with sine squared of y and now a plus cosine squared of y. Now that only came from the first two terms, so that's why I now need to end the parenthesis and still put a plus 4 cosine of y up in the numerator, and that's sine squared of y in the denominator. Now why did I think that was interesting? Because this is the most fundamental and basic of the 3 Pythagorean trigonometric identities that you guys should know. Sine squared of any angle plus cosine squared of the same angle simply equals 1. So that is definitely a simplified way of writing this answer here. So let me mess with my zoom here just a little bit, guys. All right, here we go. So now we are at, that's negative 3 times 1, so that's just a negative 3. And I think it would look nicer if I put the 4 cosine of y in front, and then there's the minus 3 all over a sine squared of y. And guys, I really don't see anything else we could do here to clean this up, so I think that is going to be our final answer. I'm trying to remember the weird notation here. That was r prime of y, and that is what we've got for our final answer right there. Now, feel free to shut this off at this point, but I said a minute ago I noticed you could do something about the original expression, that maybe you could rewrite this in a way that would be a little bit easier to deal with. Here's what I noticed. Let me switch over to, we'll go purple on this one now. What I noticed you could do right here is split that numerator and make it 3 cosine of y over sine of y, and then a minus 4 over the same denominator, sine of y. And what I noticed about that, everybody, is that that expression could be rewritten too. Now, I'm still talking about the original function, so what I'm writing here is not my derivative, it's still r of y. And cosine of an angle divided by sine of the same angle, let's see, sine over cosine is tangent, this is cotangent. So you could rewrite this as 3 cotangent of y, and then a minus 4, and dividing by sine is the same thing as multiplying by cosecant of x. Now, I really don't know if this is better or not than what I had just a second ago, but what I'm going to try to do now, guys, is play around, not like that, with this idea right here, that if that's r of y, then r prime of y, forgot my parentheses there, all right, could be written as this. It would start with 3, and the derivative of cotangent, everybody, is the opposite of cosecant squared of the same angle, which is going to be y. And then minus, we've got a 4 right here, and the derivative of cosecant of an angle is the opposite of cosecant of the angle, cotangent of the angle. So the opposite, the negative, is now going to turn that 4 into a plus, and then we would have cosecant, that should have been a y there, sorry, of y, cotangent of y. Now, what I think we have right here, guys, is a different way of expressing the same answer that we came up with right here. Let's see if I can somehow amend these two ideas. Okay, first of all, right off the bat, negative 3 cosecant squared of y. Well, that would be the same as negative 3 and, let's see, multiplying by cosecant is the same as dividing by its reciprocal. So that's negative 3 over sine squared of y. And then let's see, we've got a plus a 4. All right, I'm going to put that in. This is going to be a fraction here. We've got a 4 there, gotcha. Cosecant of y is the reciprocal of sine, so that puts a sine of y down on the bottom, and cotangent is going to be the cosine of y over the sine of y. Okay, and I don't want to spend too much time on this. This sine of y times sine of y really just makes sine squared of y, and that means that these two fractions already have a common denominator. So I've got a negative 3 plus a 4 cosine of y all over the sine squared of y, and that answer, everybody, is exactly identical to the one that we came up with right here. I just switched the order of the two terms in the numerator. So I'll leave it up to you guys which of those two methods you think is probably easier to follow. I think what I did initially in blue is a little bit more straightforward, but nobody really likes using the quotient rule. It's kind of cumbersome. Doing it, what I did in purple right there, kind of rewrites the original function and maybe makes the derivative a little bit easier, especially when you realize you could have quit right there, and I would have given you full credit for that answer. So, as I often tell you guys, if you can rewrite the original function, a lot of times, can't say always, but a lot of times, that'll make the function easier to differentiate, and your answer might be a little bit more easily obtained doing it that way.